Hi, so we're ready to start section 5.2, which is right triangle trigonometry. So there are some things I just want to review before we get started with the section material. So the first is just recalling from section 5.1, what are acute and also what are right angles, right? So remember that acute angles are going to be in between 0 and 90 degrees, right? So acute angle, so if theta is in between 90 degrees and 0 degrees, or if theta is in between 0 and pi over 2 radians, then this would be acute. Right? And acute angles are in quadrant 1, right? So acute angles are in quadrant 1, right? And that's if they're in standard position, right? So if we have an xy plane, remember to be in standard position, we have our vertex at the origin. My initial side is on the positive x-axis, and then we would be going, somewhere in the first quadrant to get theta. Right? And then the next thing that we want to review is a right angle. So remember, if we have an angle that measures exactly 90 degrees or pi over 2, that this is a right angle. Right? And, right angle, we can show that with a square, squaring off symbol, right? It's the rays are perpendicular to one another, right? So then another thing to review is what's a right triangle. So a right triangle is a triangle that has a right angle, right? So a right triangle is a triangle that has contains or no, we'll just say with a right angle. How about that? So is a triangle with a right angle. Right? So essentially if I have a triangle, then we're going to have at least one only one of the angles can be a right angle, right? You can't have a triangle with two right angles, right? Because a triangle always has three angles, and a sum of all the interior angles in a triangle are 180 degrees, right? So then that kind of is a good segue into the next part. It says if you have a right triangle, what do we know about the other two angles, right? So in other words, if I have a triangle, let's say this is my right angle, and I'll label this A, B, C, right? Those are the three angles. What we know is that angle A plus angle B plus the measure of C is going to equal 180 degrees, right? We know that. If you're taking geometry, we also know that the measure of angle B is 90 degrees, right? So in other words, B is 90 degrees. So if we fill that in, what we would have is A plus 90 degrees plus C equals 180. So then I could subtract 90 degrees from both sides and get the sum of the other two angles must be 90 degrees, right? So since A plus C has to be added together to be 90, and we know that A cannot be equal to 0 degrees and C cannot be equal to 0 degrees, right? Because if that were true, we wouldn't have a triangle. So what that tells me, with those two things combined, is that A and C are acute angles, right? So both A and C are going to be in between 0 and 90 degrees. Right? That's what we know. Right? All right, so then one last thing that I wanted to review with you is the Pythagorean theorem. Right? So if we just draw a right triangle, right? Pythagorean theorem deals with the right triangle. Then we have some terms that we have with this. So the two sides that touch the 90-degree angle, we refer to these as legs, right? So this is a leg, this is a leg, and the longest side, or the side that's across from the 90-degree angle, right? We call this the hypotenuse. Right? So what we know from the Pythagorean theorem is a relationship between the side lengths of a right triangle, right? We know that if I take one leg and square it, add it to the other leg squared, that's going to equal the hypotenuse squared, right? Or in other words, you probably have, when you learn this, probably had like this labeled as A, B, and this is C, and something else just to kind of review is that typically we use lowercase letters just to be the side links, and we use capital letters for the angle measure, right? And then you'll notice that this A is right across from this angle, right? So that would be capital A, so they go together. So like since C is right across from this angle, this would be C, capital C. And then this little b is right across from this angle, so this would be capital B, right? So let me just get rid of those. Oops. Right? So then what we could show with the Pythagorean theorem then is that a squared plus b squared equals c squared. Right. So that's the Pythagorean theorem. Right. So we're going to use that Pythagorean theorem a lot in this class. Right. So this method, the second way is probably how it was presented to you, but you just want to be sure that you can't just plug in A, B, and C necessarily. You want to make sure that C is the hypotenuse and A and B are the legs, right? That's the important piece. Because like if I had a triangle and I labeled it like this, where maybe this was side A, this is B and C, then the Pythagorean theorem here would be that A squared equals B squared plus C squared, right? It's the letters, the diagram, it matters where the parts of the diagram that it's labeled, that's more important than the actual letters, right? So you just want to be cognizant of that, right? All right, so now we want to look at some important terms of a right triangle. So we looked at some already. So if I have a right triangle, the longest side that's across a 90-degree angle, that's called the hypotenuse. And the other two sides, the ones that touch the 90-degree angle, referred to as legs. Right? Some other terms that we need. So if I have another right triangle, let's say I labeled this angle theta, then this is still the hypotenuse, the longest side across from 90 degrees. But the side that's touching the angle that we're considering, that's called the adjacent side. And this is called the opposite. Right? It's opposite of the angle. Right? So if I have another right triangle, right, and I consider this maybe angle alpha, right? So this would still be the hypotenuse. So now the adjacent side is going to be this one, right? Because it's the one touching the angle, right? So this would now be the opposite side, right? So the side that's touching the angle that we're considering is adjacent. The side that's across from 90-degree angle is always going to be at the hypotenuse, right? All right. Something else that we can talk about. So we could say, like consider the diagram, or I'll say figure below. So this is an example, right? Consider the figure below if A equals 30 degrees. List or I guess we'll just say A is 30 degrees. Let's make a statement. List the side lengths of triangle ABC from largest to smallest. Right? So let's say here's my figure. So let this be angle B, angle A, angle C. So then, that would tell me that this is side B, this is side C, and this is side A, right? Because they always go across from one another. So then if we want to list these in order from largest to smallest, I know that B has to be the biggest, right? Because it's a 90-degree angle, right? So it's kind of like thinking about it, the connection. If we know we have a right triangle, what are the other two angles? Well, if A plus C equals 90, and A or C are not able to be equal to 0 or 90, then the right angle is always going to be the biggest, right? Because A is going to be in between 0 and 90, and same with C, right? So we know B's the largest. I know that A so I guess these are listing the angles, right, in order. So I know that angle B is the largest. Angle A is 30 degrees. So angle C would have to be 90 minus 30, which is 60 degrees, right? So angle C would be the next largest angle, and angle A would be the next one, right? So we were asked to list the side lengths, right? But what I did is listed the angles first. So the side lengths, the size of the side length is going to depend on the angle that's opposite from it, right? So let me just draw, maybe convince you of this. So if I draw, an angle here, then the distance between these 2 points is going to depend on the angle in between, right? So if I have this angle versus, a larger angle, right? So imagine I have, like two rays that I'm altering the angle from it. You can see that, if this is a smaller angle, this side length is going to be smaller versus if I make a bigger angle there in between the two rays, right? So the actual angle is going to impact the side length then, right? So same thing here. If I know that B is the largest angle, then the side that's going to be the largest is the one across from the largest angle, right? So in other words, for the side lengths, little b is going to be the biggest. And then since C is a bigger angle than A, I know little c is going to be bigger than A, right? Same idea. So C is 60 degrees, so there's going to be more of an opening, so there's going to be a bigger distance for that side length, right? So that's an important thing to note, for the class. right? So make sure you're comfortable with that. And if it's not making sense, let me know, and be glad to go over it differently or with you. Right. So then the next section part here that we want to go over are the 6 trigonometric functions. So if you remember, from college algebra, from high school, a function has an input and an output, right? So with these, the input is going to be an acute angle theta, and the output is one of these 6 ratios of lengths of the sides of the triangle. Right? So, and I'll list these trig functions below, right? So something you've probably seen before, so an easy way to remember it is a saying SOHCAHTOA. Right, so you've probably seen this before. So how this helps you remember, so we have sine. So if we look here at this first one, the first letter is S for sine, so we'd have sine theta equals, and it helps remember the order, so it's the opposite over the hypotenuse, right? The O is for opposite and the H is for hypotenuse, right? And then we have cosine, right? So we show that as cosine theta is equal to the adjacent over the hypotenuse, right? And again, that order matters, right? That little saying. So C is for cosine, A is for adjacent, H is for hypotenuse, right? And then we have tangent. So that would be tangent of theta equals, we're looking here, the TOA, so that would be the opposite over the adjacent, right? So then we also have cosecant, secant, and cotangent. Right, and I'll show what these are. So cosecant, we shorthand that with CSC of theta equals, so this is actually equal to 1 divided by sine theta, right? So it's the inverse of sine, right? So in other words, it's hypotenuse over the opposite, right? So we flip it, right? Like when you divide fractions, right? It's a multiplicative inverse, right? Secant of theta is the inverse of cosine, or not the multiplicative inverse of cosine, right? So this would be 1 divided by cosine theta, right? So this would be equal to the hypotenuse over the adjacent, right? And then cotangent, we abbreviate COT of theta. That's equal to 1 divided by tangent of theta, right? So we flip tangent, and we get adjacent over the opposite, right? So I think it's pretty easy to remember cotangent and tangent like go together, but in terms of cosecant, secant, sine, and cosine, one thing that helps me is I remember, like sine and cosecant like kind of go together, so the S's and C's don't match up, right? So you'll notice that, here we got S and C together, and here's C and S, right? So again, maybe just a note, as I would just, the C's and S's don't go together. Right, might help you remember that, right? So then I want to write through an example with you. So if I have, say, a right triangle, and let's say this is theta, and so this would be the adjacent side, this would be the opposite side, and this would be the hypotenuse. Let's say that the adjacent is 4 feet in length, the opposite is 3 feet in length, and the hypotenuse is 5 feet in length. Right, so I'm just labeling that. So this right triangle actually has a special name. This is called a Pythagorean triple. Right, so Pythagorean triple is where you have a right triangle, and all 3 side lengths are a whole number, right? So if you just Google Pythagorean triple, you can see that there's a lot of examples of Pythagorean triples, and the 3, 4, 5 is probably the most common one used. So if we just go Google Pythagorean triple, right, show others like 9, 16, 25. So here's a list of some Pythagorean triples. Right, so 5, 12, 13 is another one. Right, so notice all the side lengths all have whole numbers. Oops, make sure I didn't stop recording. All right, so so if we go through this like an example, so we maybe make like a table. Right, so we have example. Right, so if I fill in sine into this example, sine of theta would be the opposite, so that would be 3 over the hypotenuse 5. So we'd have 3 feet over 5 feet. Now when you take 3 feet divided by 5 feet, the units cancel, right? So it's unitless. So we get just 3/5, right? So the 6 trigonometric functions are going to be unitless, just like we saw with radians, right? So cosine of theta is equal to the adjacent, which is 4 feet, over the hypotenuse, which is 5 feet. So this becomes just 4/5, right? Again, the feet divided by feet are going to cancel each other out. Lastly, we have tangent of theta. So tangent of theta is opposite over adjacent, right? So here's the opposite, here's adjacent. So we would have 3 feet over 4 feet, which the units cancel, we get just 3/4, right? So then remember, cosecant of theta is equal to 1 over sine theta, right? So that would be 1 divided by 3/5, right? So if I multiply top and bottom by 5/3, right, this becomes 1 on the bottom and becomes 5/3 on the top, right? So we get just 5/3, right? So we're like dividing fractions. Right? So secant of theta is equal to 1 over cosine of theta, right? So that's just the inverse, the reciprocal multiplicative inverse of cosine. So that would be 5/4, right? Just flip it, change change the 4 and the 5. And then cotangent of theta would be equal to 1 over tangent of theta, which would be 4/3. Right. So then I have kind of a question off to the side here for this diagram. So we're still using this diagram where we have theta here. This is 5 feet, this is 3 feet, and this is 4 feet. And my question is theta or 90 minus theta, 90 degrees minus theta, larger? Right? So, you know, where would 90 minus theta be? That would be this angle, right? So this angle's theta. This angle here would be 90 minus theta, right? 90 degrees minus theta, right? Because we saw that relationship. If you have a right triangle, the other two angles have to add up to 90. So if we want to know which one's bigger, think about the opposite side lengths, right? So 3 feet is across from theta, and 4 feet is across from 90 minus theta. So since 4 feet is longer than 3 feet, then that would tell me that 90 minus theta is bigger, right? And this is since 90 degrees minus theta is across from a larger or longer side than theta, right? So it's that whole phenomenon, right? So just look at that from another angle, right? No pun intended, right? So then I have just some notes here. So note that the output of a trigonometric function is unitless, like I described, right? So the units are going to cancel each other out. Also, the notation of sine theta is read as sine of theta, right? So sin with theta in parentheses is read as sine theta. And actually, sometimes, and our book does this a lot, is they don't always put the input in parentheses. So sometimes you might see just sine of theta without parentheses, right? Sometimes that gets a little confusing, where the input stops and ends, but I usually try to write it with parenthesis notation, right? But just keep in mind our book or other things might not always do that. And then the last thing, just a note here, is that the values of the trigonometric functions depend only on the measure of the angle, not the size of the triangle, right? So that's another note to consider, and I can show you, help you think about why that's true, right? So to think about this, I need to draw a diagram that kind of models this situation, right? So let me draw. So we're going to have this ray, have this ray. So we got this line segment, and then I'm going to draw another line segment here, right? And I want these are going to be 90-degree angles. This, we're going to let this be angle theta. And I can also name this as A, B, C endpoints. I'm going to label this D and E. So this side, side length I'm going to label Y, this one X. And then the line segment A to C, going to label that a length of little b. And then let me use a different color, it's getting a little busy. And then the side, or the measure of the side length AC, no, we want that AAE, sorry I didn't go far enough. This one, this guy. So this whole side here, we want that to be, I'll label that little d, right? So, and this is, I guess, part of this is a little review from when you took geometry, right? Maybe in high school, you may have talked about something called similar triangles, right? So we probably talked about similar and congruent triangles at the same time, right? But similar triangles are triangles where all of the angles are the same measurement, but the triangles are not necessarily the same size, right? So essentially, the two similar triangles have the same shape, but their corresponding sides are proportional, right? So in other words, if we look at triangle ABC, this is similar to, and we show it with this like one squiggly line symbol, is similar to triangle ADE, right? So ABC, that triangle is this guy here. Right? And if you want to see triangle ABE, that should be a D. ADE, sorry. ADE. That's like this bigger triangle, right? So that's this guy, this one in pink, right? So since that's true, I said this out loud, but let me write this down, is that similar triangles have proportional corresponding sides. Right? So that's what I was meaning. Also, just a note, that symbol means is similar to, right? At least in this context, right? So if two triangles are similar, their corresponding sides are proportional, right? So what we conclude here, so what this would tell me is that x over b is equal to y over d. Right? So I'm going, this opposite side to the hypotenuse for the small triangle. So that's going to be equal to, in the same order, right? Going the opposite angle to the hypotenuse, right? So you probably would have studied this also, like 5th, 6th, 7th grade when you talked about doing like ratios and proportions, right? Right. So as I was mentioning, with the opposite hypotenuse, so what that's looking at is sine, right? Sine has to do with opposite hypotenuse, right? We can, look at SOHCAHTOA, and sine of theta is opposite over hypotenuse, right? So since that's true, so sine of theta, if we think about it in terms of the smaller triangle, right? So, the triangle here, I'm putting blue marks in, the little one, the one I originally put in green on the outline, that would be equal to, the opposite would be x, right? Because I'm looking at this theta, right, that I labeled, which is angle A. That would be x over b, right? So that's the smaller triangle. Triangle ABC, right? And then also we can get a statement that sine of theta is equal to, so if I think about the larger triangle, that would be y over d, right? Because this one here would be the opposite, and this would be the hypotenuse, right? So this is using the larger triangle, ADE. Right? So the thing though is we already know that that these two things, we already know these two things are equal, right, from this statement. So what that tells me is that, so we could say thus sine of theta equals x over b, which also equals y over d, right? So what that does is just trying to convince us a little bit of that. So if you just reread the note, right, saying the values of the trigonometric function depend only on the measure of the angle, not the size of the triangle, right? So in other words, what this is showing me is if I have two similar triangles and one's bigger, the sine of a given angle is the same, right? It doesn't depend on the size. It just depends on the measure of the angle, right? Good. All right, so now we're ready to look at objective 2. So objective 2 is looking at evaluating trigonometric functions of acute angles, right? So we're told to, example 1, suppose that a right triangle, triangle ABC, has legs of length 6 centimeters and 3 centimeters. Evaluate the 6 trigonometric functions for angle B, where angle B is the larger acute angle, right? So these are some important things here, right? So let me first just start by drawing a diagram. Right, so we have a right triangle. So we could just I'll just let the right angle be A, this be B, and this be C, right? So we know that B is going to be an acute angle, so I know I don't want to put B where the 90-degree angle is, right? And the way this is worded, it doesn't really matter where I put A or C, but I'll just put A as the 90-degree angle. So what we're told, right, is B is the larger acute angle. So if B is bigger than C, then what that tells me is the side across from B should be larger than the side across from C, right? So, and these are the two legs. So I can either put 3 or 6 here, or 3 or 6 here, right? But again, since B is larger than angle C, then this has to be the larger side, right? So this has to be 6 here, right? 6 centimeters. So then that means that this side is 3 centimeters, right? That's what's left. And then if I want to figure out the hypotenuse, right? So this part here, the hypotenuse. If I want to figure this out, then I can use Pythagorean theorem, right? Which I reviewed with you. This is, little a is equal to what? We're trying to figure that out. So what we could find is that little a squared is equal to 3 centimeters squared plus 6 centimeters squared, right? And really, since both legs are in centimeters, a is also going to be in centimeters, so I don't have to necessarily write those units down. Just keeping in mind that everything's in centimeters might be a little easier to work through this, right? So we have a squared equals 3 squared plus 6 squared. So this would give me a squared equals, so that would be 9 plus 36, right? So 9 plus 36 is 45, right? So I have a squared equals 45. And then I would want to, take the square root of both sides, right? And typically, when I'm taking a even root, right, you should have learned that you should put a plus or minus in front on both sides, right? So what we would get is that a equals plus or minus the square root of 45, right? But in context here, a is a side length, and a is understood to be positive, right? So a is understood to be greater than 0 here, right? Because it's a side length, we can't have negative length, right? So in a very abstract sense, this would be true that we should put the plus minus here in front, but since what we're dealing with is in context of a situation where a is understood to be positive, then we don't have to write that here, right? And then another thing that you should be comfortable doing you know, from high school is simplifying a radical. So we want to take out, you know, perfect squares in here, right? So 45 is equal to 9 times 5, right? So I write it this way because 9 is a perfect square, right? It's 3 squared. So if I take, you know, like 2 and square it, 3 squared, 4 squared, 5 squared, 6 squared, you know, any of those whole numbers squared, it's going to give me a perfect square, right? So like 100 is a perfect square because it's 10 squared, right? So this would be the square root of 9 times 5. And then a property of radicals is that we can write this as radical 9 times radical 5, right? So this should have been a property that you would have studied, you know, in high school. And then radical 9 is just 3, so this just becomes 3 radical 5, right? So this is the simplified answer, right? So A is equal to 3 radical 5, right? And we're putting everything in terms of angle B here, right? So, you know, it might be easy just to write out that, maybe make like a key, that my hypotenuse is equal to 3 radical 5. And I won't bother writing down the centimeter part because remember, we're going to take centimeter divided by centimeter, and that's going to cancel each other out, right? So I'm just going to write the hypotenuse is 3 radical 5. The adjacent side would be 3 centimeters. Oops, I just said I wasn't writing that. And then, so the opposite side would then be 6, right? Because 6 is opposite from B, right? So kind of with this key here, we can just fill in all of the 6 trig ratios, right? So I want to find sine of B, right? And again, you know, if it's helpful, you know, we can write SOHCAHTOA, right? So sine of B is equal to the opposite over the hypotenuse. So the opposite is 6. The hypotenuse is 3 radical 5, right? And this will simplify, so 6 divided by 3, we get 2, right? So this would be 2 over radical 5, right? Another thing, though, with simplification is we don't want a square root, a radical, in the denominator, right? So we need to do what's called rationalize the denominator, right? Which would be multiplying top and bottom by radical 5, right? So radical 5 times radical 5 just gives me 5, right? Because that would be the square root of 5 squared, which they would cancel each other out. And then on the top in the numerator, we would have 2 times radical 5, which is 2 radical 5, right? So that would be my final answer for sine B, right? So then cosine of B is equal to the adjacent over the hypotenuse. So the adjacent is 3, hypotenuse is 3 radical 5, right? So similarly here, you know, the 3 divided by 3, those can cancel out, so we just get 1 over radical 5, right? We can divide top and bottom by 3. And then same idea, I need to rationalize the denominator, so I'd multiply by radical 5 over radical 5, which gets me to radical 5 over 5, right? So that's the answer for cosine of B. Tangent of B is equal to the opposite over the adjacent, right? Again, just pulling that from the SOHCAHTOA helpful tool. So then the opposite we found to be 6, adjacent is 3, so that leaves me with 2, right? So tangent was easier to find because we didn't have to do any, we didn't have to rationalize the denominator at all, right? So then the other 3 trig functions just kind of follow from these first 3, right? So, you know, we want to find cosecant of B. So cosecant of B, remember, is 1 over sine B, right? So it's just the reciprocal of sine, right? So what I'm going to do, though, is use this version that sine was equal to and just write it in this fashion. So we just flip that and we get radical 5 over 2, right? So the reason why I did that is I don't have to do any type of rationalize the denominator, right? So if I pick the version that has the radical in the denominator already, then when I flip it, the radical will be in the numerator then, right? So that's just convenient. It's helpful. So then secant of b, right? Same idea. That would be radical 5 over 1, or just simply radical 5, right? And then cotangent of b would be 1/2, right? It'd be the reciprocal of 2, 1 over tangent. Oops, I didn't write these out specifically, but secant of beta, right, is 1 over cosine of beta, and cotangent of beta is equal to 1 over tangent of beta. Or b, that's a b, not beta. Sorry. Beta, it kind of looks like a b, but that's the Greek symbol. Right? All right, so I think we'll keep going here. So I'll go for about another 15 minutes or so, and I think I'm going to split this section up too. I hate to do a video more than an hour. So maybe get through this next example, and that might be a good place to stop for this video, right? So example 2 says, suppose that sine of theta equals 3/4 for the acute angle theta. Evaluate secant of theta. Right? So if we know that sine of theta equals 3/4, right? What we're trying to find is what is secant of theta. Right? That's what we're told. So we need to try to figure out how to do that, right? So where to start is thinking about, well, sine of theta is equal to the opposite over the hypotenuse, right? Remember our good old SOHCAHTOA, right? So if I start to draw a picture of this, let's say this is theta. So this was, equal to 3/4. So the opposite of theta was 3. The hypotenuse was 4, right? And it could be, these could not be the exact side lengths, right? Because remember, the trig functions don't depend on the exact side lengths; they depend on the angle, right? We looked at that, how a bigger triangle and a smaller triangle, but this is just one version of a triangle that could work in this case, right? But I could, multiply all the sides by 3 or 4 or 5 and get a bigger triangle, and it would still work just fine, right? But that's not really necessary, right, here. So then what I'm missing, though, is this side. So we can call this just, let's say, x. Right? We don't know what x is, this side length, right? But secant of theta is equal to 1 over cosine of theta, right? Cosine of theta is adjacent over the hypotenuse, so this becomes the hypotenuse over the adjacent, right? That's how we find secant, right? So secant of theta is equal to the hypotenuse divided by the adjacent side. So if I just fill in, my hypotenuse is 4, my adjacent side is x. I don't know what x is, so I need to figure out what x is. So x, we can figure out using Pythagorean theorem, right? So using Pythagorean theorem, we would have that x squared plus 3 squared is equal to 4 squared, right? So that would give me x squared plus 9 equals 16. Then I could subtract 9 from both sides, and we get x squared equals, so 16 minus 9, we get what, 7? So then take the square root of both sides, we get x equals radical 7, right? And that's simplified, right? Because 7's a prime number, right? So then what secant of theta is equal to is 4 divided by radical 7, right? But I want to rationalize this denominator, right? I don't want a radical in the denominator, so I multiply both sides by square root of 7 over square root of 7. And what this gives me is 4 radical 7 divided by, so radical 7 times radical 7 would be 7, right? So what we have then is that secant of theta equals 4 radical 7 over 7, right? That's what we were trying to find. Right? All right, so I think that's a good place to stop in this video. So we're at 50-minute mark. So I'll keep, keep making videos. This section might need to be 3 videos. We'll see. But if you have questions, don't forget. Please let me know. I'll be glad to help. Thanks.